Alright, in this video we're going to look at some additional reactions of ketones and aldehydes. The first one we're going to look at is acetal and hemiacetal formation. Okay, when an aldehyde or alcohol, when an aldehyde and alcohol encounter each other, an equilibrium is set up, okay, where you form this structure here called a hemiacetal, okay, at equilibrium. This is analogous to hydrate formation, which occurs when water interacts with an aldehyde or ketone. This process is accelerated by acid. Normally hemiacetals are not stable. If you remove the alcohol, they spontaneously revert back to the carbonyl compound, but there are quite a few examples of stable hemiacetals that we'll briefly mention later. Okay? If one does this reaction in such a way that water is ejected from the system as it's formed, okay, and in the presence of acid, a further reaction can occur where we make an acetal, okay, and water. The acetal is a stable compound, okay. It can be isolated. In the presence of acid or water, the acetal and the alcohol plus carbonyl compound are in equilibrium, okay, but without the acid present, the acetal can be isolated in pure form, okay, and if the acetal is treated with aqueous acid, it simply goes back to the original aldehyde or ketone and alcohol. Okay, all right, so what we see here is that the acetal formation reaction is in equilibrium. Going to the right, it's acetal formation. Going to the left, it's acetal hydrolysis. This reaction is controlled by Le Chatelier's principle. Okay, so if you do the reaction in such a way that the concentration of water is minimized, okay, the reaction goes this direction, and if we maximize the concentration of water, the reaction goes that way. Okay, so if we treated this ketone here, cyclopentanone, with pure methanol and H+, we could expect to make the acetal. Because we're using methanol as the solvent, the number of methanol molecules is huge compared to the number of cyclopentanone molecules, or compared to the number of water molecules that are going to form as a byproduct of this. So this is one way to control the equilibrium, to just use the alcohol you intend to incorporate into the acetal as the solvent. Now we're going to treat it with aqueous acid. H3O+ is what we're looking at here. Usually the pH is about 1 to 2 is required. Not super strong, but relatively strong acid. This will take the acetal back to the carbonyl compound. Okay, so here we see another acetal formation equation. This is ethylene glycol. This is frequently used to make acetals. This is a particularly stable acetal because it's cyclic, and the last step in the mechanism we're going to see is intramolecular, and that's somewhat favorable, and its hydrolysis produces the original ketone plus ethylene glycol. Okay, an important thing to note about acetal carbons. Okay, if you look at the functional group, there's always one carbon that contains 2 oxygen atoms on it, and that's the group that corresponds to the carbonyl group if the acetal were hydrolyzed. Okay, so let's do a retrosynthesis question here. Let's think about which carbonyl compound is required to produce each of these species. And again, you should try this on your own. Pause the video and restart it. After you've done that, I'll go through the answers right away here. All right, so what we want to do here is we want to identify the carbon that's going to be a C double bond O in the precursor compound. Okay, and that compound's quite easy to identify because it has two oxygens on that carbon. Okay, that carbon rather is easy to identify. Okay, here, this is going to be the carbonyl compound in the product. Okay, all right. And so this is the precursor compound for the first reaction. Okay. And note how the asterisk carbon, again, corresponds to the carbonyl group. And this is the precursor compound in the second example. Okay. All right. Let's look at the mechanism here for acetal formation. Okay, so first we make the hemiacetal, and I'm not going to go through this mechanism because it's totally analogous to hydrate formation. Exactly what happens with water also happens with ethanol, as long as the acid is not overly strong. Okay, but this reaction can go further. Okay, so we protonate this alcohol. We now generate a leaving group, water. Okay, we can use the lone pair with this oxygen to push water out. Okay, and that gives us this compound. Some people refer to this as a carbocation. Okay, let's just look at that. That's a resonance structure that you could write for this. In this form, it's an oxonium ion. In this structure, it's a carbocation. Okay. All right. Now we have, because we're doing this reaction in ethanol as a solvent, we have a lot more ethanol molecules than we do water molecules. Okay, so an ethanol molecule comes along and adds to the carbocation or oxonium ion to make this, and then we just lose the extra proton to form the acetal. Okay, the reason this reaction is going to the right here is because we're doing it in ethanol, and the amount of ethanol molecules is huge compared to the amount of water molecules produced in that first step there. Another way that this is commonly done is to do it at heat, and move water through what we call azeotropic distillation. Okay, so if you run this reaction in benzene, which is not the most environmentally friendly solvent, what happens here is that water and benzene form a low boiling azeotrope, and you can usually get rid of the water because it's lower boiling, and you can take it out of the system as it forms. This is a common technique that's used to drive the reaction to completion. The device that allows you to do this is called a Dean-Stark trap. I don't want to get too much into the design of apparatus, but this is a very common technique that people will use during acetal formation reactions. Okay, let's look at one of the special uses of acetals. All right, so look at the transformation here at the top. Most of us understand probably that this could not work. The first step is designed to produce this compound, and this compound could not be stable. Okay. It requires that we have a carbonyl group and a Grignard reagent in there together, and these are not compatible with each other. So this reaction would fail because this Grignard reaction that I circled here is not a stable compound. Okay? It would not sit around and wait for someone to add the second carbonyl compound. But we can use acetals here to carry out this reaction. Okay, so what we need to do is temporarily inactivate the ketone. Okay, so we must temporarily inactivate this. Okay, and acetals are an excellent way to do this. Acetals are ethers. They don't react with Grignard reagents. They're also very easy to turn back into ketones through acid hydrolysis. So if you wanted to do this transformation, you could do it very easily just by making the acetal. Okay, and this one's a relatively easier one to make because it has the intramolecular system going for you. Okay, and so once the acetal is made, it can react with magnesium ether, and now this Grignard reagent here, this one is okay. Okay, there's no problem with it. An ether and a Grignard reagent can exist as part of the same molecule. All right, so now this Grignard reagent sits there, waits for somebody to add acetaldehyde. This makes this, and then this reacts. Sorry, I covered up the H3O plus. I'll write it again, H3O plus. And this gives us our product. Sorry, here's our product. Oh, okay. Okay, all right, so, and this will work. This will be a perfectly acceptable way to convert that ketone bromide into the corresponding ketone alcohol. All right, let me just say one thing about this equation before we move on. There's some H3O plus here, and there's some H3O plus there. The H3O plus used to quench Grignard reactions is usually very weak acid. Often it's just plain old water. Often it's also saturated in H4Cl. Okay, so this is not strong enough to cause the acid hydrolysis. I guess technically you could hydrolyze everything, but usually it's best to do this in 2 steps because you can purify at each stage. Okay, so the acid that you see used to quench Grignard reactions and lithium aluminum hydride reductions and things like that usually is not very strong acid. You need a separate step to accomplish the hydrolysis of the acetal. Okay, how do we carry out this transformation? All right, most of us remember that sodium borohydride is a very mild reducing agent, but it will only reduce ketones in the presence of acids, right? Okay. All right. If we tried to add a large excess of lithium aluminum hydride, this is what we would get. So this wouldn't be very effective either. We could think about oxidizing back, but then there's a selectivity problem of which alcohol gets oxidized. Okay, but we can use acetal protecting groups to our advantage here, because the acetal protection is going to only occur at the ketone group. All right, so you could treat this with ethylene glycol and a little bit of mild acid. We would get this acetal. The acetal would then react with lithium aluminum hydride. This is our only carbonyl group that's reactive to, it's the only carbonyl group present. It'll react with lithium aluminum hydride to reduce this all the way to the alcohol, and then our acetal hydrolysis will give us the desired product. Okay, so this is the last two slides. What we've seen is an example of an acetal protecting group protocol and how it can help you do difficult transformations of ketones and aldehydes in the presence of other functional groups. Okay, this is the last reaction we'll look at in this video. This is called cyanohydrin formation. Okay, so if we treat a ketone or aldehyde with sodium cyanide, then H3O plus, we make a cyanohydrin, and this is a molecule that has an OH and a cyanide on the same carbon. The cyanohydrin is stable at neutral or acidic pH, but if you treat one with base, it'll revert back to the starting materials. Okay, so NaOH will transform it back to the carbonyl group. All right, so the mechanism involves reversible addition of cyanide to the carbonyl group. Okay, and this particular reaction is not favorable. The equilibrium goes to the left, and this is because of the pKa difference between cyanide and alkoxide. An alcohol typically has a pKa around where water is 16. Hydrogen cyanide has a pKa of 9. So if you just look at this from the base strength, it's more favorable for this reaction to go to the left. Okay, but if we add some acid, we can capture this minor species at equilibrium, and this will successfully form our cyanohydrin and water. Okay, and you see here why this reaction, why cyanohydrins are not stable in the presence of base. If this acid isn't here, or if you're under basic conditions, you make this alkoxide, and this alkoxide, remember, wants to revert back to the original carbonyl compound. Okay, so the cyanohydrins are stable at neutral or acidic conditions, but not under basic conditions. Okay. All right, so let's complete these reaction equations. Let's predict the product of each reaction. All right, so here we have a aldehyde group that's going to react with our cyanide followed by aqueous HCl, and that's going to produce this compound. Note that this is a chiral center, and we already had one that wasn't defined, so I assume it's a racemic mixture, and this would produce a mixture of two diastereomers. I'm not sure if there's any selective formation of one over the other. Okay, and the second one is a retrosynthesis. What is the precursor compound? Okay, so we need to identify the cyanohydrin carbon, and that's this one. And the cyanohydrin carbon is the one that will be the C double bond O in the starting material. So we simply need that compound right there as our starting material. Okay, and let's look at one last slide here, and this is kind of a practical slide. All right, many of you have heard the expression, don't eat the seeds of apples and cherries and peaches and plums and things like that. Well, because they contain cyanide. Well, they do contain cyanide. They contain cyanogenic glycosides. An important cyanogenic glycoside is laetrile. This was 20 years ago thought to be an active anti-cancer drug. It was never approved by the U.S. Food and Drug Administration, but other countries had approved it for treatment, so people were going to other places to get treatment. It's now been debunked, but its mechanism is very practical. It's easy to understand. Metabolism is going to take this carbon here, which is an acetal. Note that it has two carbons, and it's going to turn it into glucose, a perfectly harmless compound. Okay, but it's also going to generate the cyanohydrin, and the biological pH is 7.2. It's slightly basic, so it's thought that laetrile will generate this highly toxic compound, hydrogen cyanide, in the cell, and that would kill whatever cell this process was occurring in. Okay, and it sort of nicely ties together the things we've been talking about concerning acetals and cyanohydrins. Okay, all right, so just one other thing here. Let's see. We're going to notice that this is a hemiacetal, yet I'm drawing it as a stable compound. All right, so one class of hemiacetals that are stable concerns those that form 5 and 6 membered rings. Okay, so in these type systems, you often do see the stable hemiacetal, and a much later chapter in this course concerns carbohydrates. And we're going to revisit this issue of unstable versus stable hemiacetals when we look at carbohydrates more deeply, kind of toward the end of the class. So I'm going to stop this video here. Okay, let's see. Yeah, so that's the last of it.